So, what I'd like to do is start off just talking about Born's rule, just to remind people about what that is. Talk a little bit about why there seem to be so many people who want to do something with it, and then get into Gleason's theorem and these other two papers. That sounds fine by you.
That sounds like a plan, or
Okay.
plan-shaped entity.
All right. So here's my cartoon of quantum physics, right? We have, generally, people like to break it up into two parts. We have this nice deterministic evolution of this thing called the wave function that comes about from the Schrodinger equation. And then every once in a while, there's some measurement that comes along. And all of a sudden, you have this irreversible event that happens. Not everybody who does quantum foundations thinks that's a great description of it, but that's the way it's normally taught to you, right? And the Born rule is basically taking this Schrodinger equation that's evolving this quantum state and saying, okay, well, we're going to apply some math, we'll get some probabilities, and after that, we'll find out what the state is afterwards. So that's basically the place of the Born rule, as far as I understand it, in quantum mechanics. This is one of these things where the Born rule isn't actually what they never say this is the Born rule in your undergraduate, or I didn't even hear it in my graduate class in quantum physics. So it's just something that shows up a little bit later. Somebody actually tells you somebody made this up at one point, right? At the beginning, they're just sort of saying, well, this is obviously right what happens, and here's all this fun math that you get to do for the next 3 months. But there's actually something going on behind it, and it's pretty interesting. So I think the first thing I wanted to do is see how much of that do you agree with or disagree with? Because I thought this was fairly standard, and then maybe the third time I read your paper here, it sounded like you might have some issues with some of the way that is presented. Is that okay, or is there something it seems like there might be something I'm missing in that cartoon?
As cartoons go, I think that's a fairly good one. This is, of course, a topic where it's very easy to slide off into a fog of confusion, and I think it was aptly summarized by Adon Cabello when a few years ago he made a chart of the different so-called interpretations of quantum mechanics and tried to classify them to at least a first approximation kind of way. And the title of his paper was A Map of Madness.
Okay. No, that's very good, yeah.
And I found that quite fitting. And of course, you have further problems where not everyone who pioneered the subject actually said the things that they are generally attributed to. I didn't actually say the things that have been attributed to them, because physicists are very sloppy about history. So there's just complications upon complications when we talk about these things. And it's interesting to think about why that has happened in quantum mechanics so much more than anywhere else in physics. If you stack up the literature on interpretations of quantum mechanics and compare that to interpretations of special relativity, interpretations of thermodynamics. And of course, people do talk philosophically about special relativity or thermodynamics, but the general level of confusion with quantum mechanics is just vastly, vastly greater. And one of the challenges I think that has contributed to that over the past 100-ish years is with a subject like special relativity, we have Einstein's postulates. And basically we can just spell out the theory in words. You can say a lot about the theory and what's the most important features of the theory by saying inertial observers will agree on the laws of physics. inertial observers will agree upon the speed of light. And then from there, and by inputting a little bit of math about coordinate systems and such, you can then derive all the formalism of the theory. And then when you're in the middle of a calculation in special relativity, you can always refer back to Einstein's postulates and get that qualitative check upon your reasoning and go, oh, whoops, suddenly I've broken Lorentz invariance. I've done something horribly wrong. And so we just have a better conceptual grounding of the theory upon postulates with a transparent physical meaning. Whereas, and you hinted a little at this in what you said, when we teach quantum mechanics, we kind of dump a few chapters of linear algebra and functional analysis upon the poor student and say, here, have fun.
Yeah.
And we don't do that out of cruelty, or not just out of cruelty. It's because we don't have much of a better clue. We don't have the counterpart of Einstein's postulates for special relativity or the 4 laws of thermodynamics. What are the 4 laws of quantum mechanics? Can we say them in a way that doesn't depend upon the elaborate successive levels of mathematical sophistication that we build up in the textbook development, in the ordinary development of the theory? And this has been a problem which has vexed people who care about such things since the early days of the subject, in some fashion or another, going back to von Neumann is generally credited as being the first to sort of thinking along these lines. Where does the math of quantum theory come from? From what list of physical and logical postulates can Hilbert space and vectors and Hamiltonians, unitary operators, a Schrodinger equation, tensor products, eigenvectors, eigenvalues, positive operator value measures, from what list of the 4 laws or the analog of Einstein's postulates can all that be derived? And if we knew that, we could maybe say things like, okay, if we ever have to modify quantum mechanics for any reason, well, then we might actually know what we can change and what we have to keep.